Swayam Prabha. Digital India. Educated India.
Hello, welcome to lecture 7. In this lecture, we shall be completing the discussions on impedance transformation that we had discussed in the last lecture. So in the last lecture, we had discussed some very simple impedance transformation circuits, but here we will be considering a bit more complex. So before going into the actual circuits, let us spend some time in discussing the Smith chart. Yeah. So okay. So let us first see what a Smith chart is. So this is the actual commercial ZY Smith chart. These blue lines represent the constant conductance and constant susceptance circles. The red ones represent the constant resistance and constant reactance circles. The lines, there are 3 scales, or rather there are 4 scales actually if I zoom in a bit. So there is one which is the angle, just the pure angle of the circle. So 90 degree corresponds to here, 180 degree corresponds to this. This is minus 90 degree. Other one is the wavelength, this top one. So this is the top one is for distance in terms of wavelengths. If I move towards the generator, because when I move towards the generator, I move in the clockwise direction. And the bottom scale here is the distance in terms of wavelength when I move towards the load. And then these red and blue markings are the reactance and susceptance corresponding to the constant reactance and constant susceptance circles. And then the constant resistance circles are marked here in red and the constant conductance circles are marked here in blue. So suppose if I go say from this point, so let us go back to the problem that we discussed in the last lecture. So we have a load Y which is 0.5 minus J 1.0. So recall that so this is the admittance. So we will, if we plot it using the admittance Smith chart, which point will it correspond to? So first of all, because it is negative susceptance, it will be in the upper half of the Smith chart. 0.5 minus J 1.0. So let us locate 0.5 conductance. So this one is the, and minus J1 is the, this corresponds to this one. Okay. So we have 0.5 minus J1. So this point corresponds to the susceptance Y. Okay. 0.5 minus J 1.0, and then if we add in admittance YC in shunt, then what happens? So in the last lecture I described that this is like a movement along a constant conductance circle downwards. But how much do we move? So we have to move by a total impedance. We have to move along a constant conductance circle, so that the susceptance changes from minus 1.0 to minus 0.5. So see, we can locate this. So we had this 0.5 minus J 1.0, and then we moved along this line till we came here. Okay, so this is the point. So in terms of the actual Smith chart, we start here and move till here. So that's how we do this actually in a Smith chart. Okay, so now let me go back to the circuits. So the 2 other circuits that I wanted to, it's not just 2, there are a number of other circuits. So suppose we start with Z equal to 0.5 minus J 1.0, okay, and say we want to match it to 50 ohm. So here we are actually matching it. So you see that a single component either in series or shunt is not enough to transform both, right? So we have to start from here, 0.5 minus j 1.0, and what we finally need is z equal to 1 plus j 0. So then how do we do that? So we are starting here and we have to reach here. So this, after addition of the impedance matching network, whatever be it, so we have to have a final impedance of 50 ohms. So let me try to show this. So let's go back to the problem which we were describing. So the problem is that we have a load Z. So in terms of the Smith chart, it's like this. Okay. So Z equal to 0.5 minus j 0.5. So that will be somewhere here. So this is my, say my point, say my R equal to 0.5 circle, and this is my, say, Z equal to minus 1. Sorry, X equal to minus 1. And this is R equal to 1 circle. This point corresponds to okay, and we have to obtain 50 ohms. So 50 ohm in terms of normalized. So this here um, should be here. Okay, and that should be equal to 50 ohm. So in terms of normalized Zin should be equal to 1. Okay, so how do we do that? So one way, as this we see, if we first add an inductor and then a capacitor, then if we add an inductor, we can go along a constant resistance circle, okay, till a point, certain point say, and then follow a constant conductance circle till we reach that point. Okay, now this point, say, what should be the value here? Okay. Now here, all along this constant resistance circle, my R equal to 1, right? And R equal to 0.5, I beg your pardon. And this point here the constant reactance circle passing through this point is x equal to 0.5. Okay, and at this point, if I see this point, so this point is, in terms of z, it is 0.5 plus j 0.5, and in terms of y, it is 1 minus j 1.0. Okay. Now we see we have obtained the correct real part, isn't it? At this point, we need this point that we have to achieve as, in terms of impedance, it is 1 plus j0. So now we have to add something that will cancel, something in shunt that will cancel this one. So this is, as you can see, this is inductive, isn't it? Negative this is admittance, and this is negative here. So if negative admittance means inductive. So to cancel it, I need capacitance ZC of value of admittance value plus j 1.0. So this path along a constant conductance circle here. So say this is my using a constant conductance circle passing through this point. Then the value of the conductance G is 1, and the reactance, the susceptance that is added in shunt causes this point to move here. Okay, is that clear? Let's see, the path that is followed is like this from here and then like this. Okay, so this is how we can design the impedance matching network. Now for this we can have another path also like this one. Okay, so here this is z equal to 0.5 minus j 1.0. I have to go here, so I can. So instead of going like this and then coming back like this, what I did is, or what can be done is, I go along a shorter path like this. So here I'm going upwards, so I will have to add inductor in series. Okay, so here, say my original Z is minus j 1.0, and first I add an inductor like this. Okay, it means the black. Okay, so that this inductor corresponds to this length. Okay. So here the value, so I would urge you to find out the value of this inductor. It's given in the slides, and then I follow a constant conductance circle like this, but this is also upwards, so that means it is inductive. In the previous one we had the shunt admittance to be capacitive, here we have it inductive. Okay, so please try to find out the values of this this inductor and this inductor. Let's see a different case. Now suppose the let's consider this one. Suppose instead of the initial starting point lying at the bottom hemisphere, say we have the starting point lying in the upper hemisphere. Okay, so again this is our Smith chart. Say we have a point here, so this is 0.5 plus j 1.0, and again I have to bring it to the origin, this point. Okay, so one way to do it is, again I travel along a constant resistance circle. So whenever I travel along a constant resistance circle, I'm adding a series impedance. Whenever I travel along a constant conductance circle, I add a shunt resistance, a shunt admittance, I beg your pardon. So see here, if I travel along, so one path that I could travel is this. So this part corresponds to a series impedance. Okay. This part corresponds to a shunt admittance. Okay. Now, what does this series, what is the value of this series? Now look, if this point, at this point, okay, my value of the, see, if I go along this constant resistance circle, my real part of impedance doesn't change. So at this point my Z will be, so this point corresponds to this part. Say I call this Z dash. So Z dash will be equal to 0.5, then 0.5 plus j 0.5. Okay, so I have added what I have done, I have added a negative reactance so that this value becomes this value. Okay, so the negative value is, so negative reactance means a capacitor. Okay, so the impedance matching will be something like this. So I started with 0.5 plus j 1.0. I added a capacitance minus j 0.5. So now here I have, what is my impedance value? It is 0.5 plus j 0.5 here. Okay, and then finally I have to now, so what does 0.5 plus j 0.5 in terms of admittance correspond to? So I have at this point Z dash equal to 0.5. So this means this is Z dash or Y dash. Okay, 0.5 plus j 0.5. Okay, now the corresponding admittance is one minus j1. Okay, so see, I have already obtained the correct real part. I have to cancel this imaginary part, and to cancel, so this is negative means this is inductive, the susceptance is inductive. To cancel it, I have to add a shunt capacitor So this is ZC1. You have to add a shunt capacitance, let's call that YC2, and that should have a value of plus J1. Okay, so this is my circuit. Now note one thing before moving on. These are the normalized values. Okay, so the actual reactance of this capacitor will be minus J.5 into Z0. This is important. Okay, please don't make this mistake. So don't forget to actually denormalize the values. Okay, that is important. Now, so this is one path that we could follow like this. What is the other path that we could follow? We could have followed a path like this. So this was our starting point. We could have gone like this and then like this. In this case, the first part, the series reactance remains capacitive, but since the shunt path is going upwards, so it will be inductive. In that case, the impedance matching circuit will be like this. So this is Z equal to 0.5 plus J 1.0. This is ZC minus 0.5, and then this is for the previous problem. Yeah, so I leave it as an exercise for you to find out the values of the capacitance and inductance. That will enable you to go first from here along a constant resistance circle to this point, and then along this path along a constant conductance circle to the origin. Try to find it out. So now there are some regions which are forbidden. What do I mean by forbidden? For example, say you have a load ZL like this, and you want input matching network like this. Okay, fine. But finally get now, and say you need another matching network like this. Then what you will observe is that if we have a Smith chart, okay, then this region this is what is known as the forbidden region, because if you have any ZL within this region, then that cannot be matched using either of these two circuits. Okay, now for example, let's say if you are at this point, so and you choose any of these two circuits, Then if you have a series, you see that in both of these circuits we have a series inductor. The series inductor means we have to go upwards, right? Now if we go upwards, we can never reach any constant conductance circle. Okay. Let me redraw it. If you are in any of these, say you are in this region, having a series inductor first means you have to go upwards along a constant resistance circle. And if you go along a constant resistance circle, then you can never meet a constant conductance circle which goes to this point. Okay, that's the problem. Similarly, say if this shaded region is the forbidden region for this kind of circuits, what will be the circuits where this region is forbidden? Try to work that out. So, this is the first part of this lecture.